we are taking the revision of these all examples. So, simple stresses and strains. As already discussed, simple stresses and strains. This concept is related with any engineering material, any mechanical component, any element, any structural element, inside which, if suppose we are considering, if we are applying the amount of force P, as considered P is the force, this notation we are using. Secondly, if suppose L is length, if suppose A is cross-sectional area, we are considering A as cross-sectional area, and if E is the Young's modulus of the material, then if suppose P amount of force is applied on any bar, suppose we are considering any bar, so for this bar P is the amount of force applied. Either force is tensile in nature or compressive in nature. If we consider here P as tensile in nature, then in this case we are considering, we are identifying elongation of this bar. For that purpose we are considering if dl is the elongation, then this elongation and its original length L, with that relation we are calculating strain is equal to change in length upon original length. So change in length we are considering as equal to dl, and original length notation we have given as L. So dl upon L will be considered as strain in the material. Similarly, if we are interested to identify the stress, then if suppose sigma is the notation we are using for denoting that stress is always equal to force upon area, and we have used P as notation for force and A as area. And if D is the diameter for the rod, if suppose we are considering this bar having diameter D, then area will be calculated based on this diameter as A is equal to pi by 4 d square. So stress will be considered as force upon area, where area is equal to pi by 4 d square. Secondly, if suppose any bar with cross-sectional area different than this round specimen, if suppose we are considering the cross-sectional area like this, T is the thickness and B is the width. For this, if suppose force P is applied on both sides, then area will be calculated based on this force. Suppose here area is based on this thickness into width, and then the stress value sigma value will be force upon area, where area is equal to thickness into width. So this is about the simple formulas of stress as well as strain. If we are interested to identify the elongation present inside this bar, maybe that bar is cross section is round or this cross section is rectangular, then in that case this elongation dl will be considered as p l upon ae. So elongation due to application of force P having original length L, cross sectional area A and Young's modulus of material as E. We are considering PL upon E, where force P is measured in terms of Newton, length is measured in terms of millimeter, cross sectional area is measured in terms of mm square, Young's modulus as well as stresses that will be measured in terms of Newton per mm square. Is it okay? So this is one of the type or first type of example in simple stress and strain in order to identify the stresses as well as strains in any component if cross-sectional area is known. In that, variety may be in terms of if suppose cross-sectional area is changed, or in this bar if I am making any round hole likewise, and if it is asked to identify the stress as well as strain in that particular round bar, then we will have to consider the reduced area. If suppose we are considering this diameter as D1, D is the original diameter of this round bar, and if suppose D1 is the diameter of this hole and force P is as it is, then once again when we are trying to identify the stresses present inside this round bar, in that case we will have to consider this reduced area into consideration. Means what? If we cut this particular section here, then after cutting this section, what will happen if I am taking the perspection of this cutting position or cutting plane, if I am cutting this one here, then this particular portion after cutting will look like this one. So this particular portion will be available after cutting this bar, and then we will have to require to take into consideration this much area only. So this much area will be considered as area for calculation of stress. Is it okay? So stress upon strain, likewise this particular portion will be cut, will reduce from this particular bar. If suppose this is a rectangular, this will be cross section, and if this is a round bar, then in this round bar, this particular portion will get cut and the remaining area will be taken into consideration. If suppose we are taking hole here in this section, then in that case this particular area will taken into consideration, and this much area which is present to cutting the hole will get reduced. Means in that case, if we take its cross section and if we take here the perspection from this side, then definitely this much area will have to take into consideration. Means if we have considered this T as total thickness, and if we consider this D1 as diameter for this hole, then D1 will get subtracted from this T, and then what will be the reduced area in that case? what area should we consider while calculating the stress? So while calculating stress, in that case, as usual, force upon area P will remain as it is while calculating this cross-sectional area A. Now from this total T thickness we will have to reduce D1. Is it okay? Then what will be cross-sectional area? T minus D1 and width B will be as it is. So if we are considering plane bar, P upon cross-sectional area, this T into B is sufficient. But if we are taking a reduction inside this cross-sectional area by taking any hole, then this reduced area will have to take into consideration, and this cross-sectional area A will be T minus D1 into B. Is it okay? So T is total thickness, and this particular D1 we are subtracting from this one, and B is the width of this bar. Then reduced area will be considered as T minus D1 into B, and then the value of stress will be different for this case. Is it okay? Similarly, if we take one more example, that suppose bar is hollow bar. In simple stress strain example we are considering, and in this example, suppose we are taking one hollow pipe like this one. This is any hollow pipe. This is the portion of this hollow pipe. We are taking this cross-sectional area from this hollow pipe. We are showing here this as cross-sectional area. Suppose this one is the outer diameter, DO we are considering here it as outer diameter, and if suppose DI is considered to be inner diameter, DI is considered to be inner diameter, then for this particular hollow pipe consisting of DO as outer diameter and DI as inner diameter, if we are applying suppose force, or this force, the nature of force, if it is compressive in nature, suppose I am considering this force along its axis, if this is the axis of this pipe, and this force is applied along its axis and this is compressive in nature, and in that case also stresses and strains will get calculated with this particular which is present area. So in this case stress sigma, once again force upon area, the force P is considered as compressive force and cross-sectional area. So this cross-sectional area will be area perpendicular to the application of force. So sigma is equal to this P force which is compressive in nature, and cross-sectional area that now considered as pi by 4. Outer diameter is DO its square minus inner diameter DI its square. So stress sigma in that case will be P upon pi by 4 DO its square minus DI its square. Okay. So this is one different kind of example in simple stresses and stress, how to identify the stress as well as strain and elongation. This is the first type of example in which we have to calculate stress, strain as well as elongation when different cross-sectional areas are available. Okay. So this was the first kind of example inside our simple stresses and strains. The second type of example which we have seen in this simple stress and strain, in that the second variety of example we have considered as bars of varying cross section. This is second type of example which we have studied in simple stresses and strains. So as we know that bars of varying cross section, if suppose I am taking this example, this is bar of various cross section. If suppose cross sectional area is varying here, if we consider this as section 1, we are considering this as section 2, and we are considering this as section 3. If this diameter we could consider as D1 is the diameter, if suppose this diameter is D2 is diameter, and suppose this one diameter we are considering as D3. Similarly, if suppose we are considering this length for section 1 as length L1, suppose this length for section 2 we are considering as length L2, and if this length we are considering as length L3. And if suppose a tensile force of magnitude P is applied for this bar of various cross section, then in that case the total elongation, if suppose we are considering DL as total elongation present inside this bar, and if DL1 is considered to be elongation present in section 1, we are considering this part as section 1, this part as section 2, and this part as section 3. If DL1 is the elongation in section 1, if we are considering DL2 as elongation in section 2, if suppose we are considering DL3 as elongation in section 3, then total elongation present inside this bar due to application of this tensile force P will be DL1 plus DL2 plus DL3. So total elongation DL will be considered here it as DL1 plus DL2 plus DL3. Now the DL1 as we have considered as elongation in section 1, DL2 is considered as elongation in section 2, and DL3 as elongation in section 3. So how could we identify the value of DL1? As usual, this DL1 will again depend upon the applied force P, length L1, then cross sectional area A1 and Young's modulus E1. As here D1, D2 and D3 are different, so cross sectional area A1 will get calculated as A1 is equal to pi by 4 D1 square, A2 will be calculated as pi by 4 D2 square, and A3 will be calculated as pi by 4 D3 square. Then DL1, as usual, our conventional equation to identify the elongation DL, always we are writing as DL is equal to PL upon AE. That means elongation is directly proportional to the applied force, original length, and inversely proportional to cross sectional area and Young's modulus of the material. If suppose section 1, section 2 and section 3 consists of same material, then Young's modulus will be same for section 1, section 2 and section 3. As force is P, so P is remaining same, and Young's modulus being E, if that Young's modulus as material is same, we are considering as same. The changing thing is here only length and cross-sectional area. So if we are considering that material is same, with that assumption we will consider dl1 is equal to P upon E, only change will be there, length L1 upon cross-sectional area A1. Similarly, elongation in section 2 dl2 will be PE into bracket L2 A2. We are considering P applicable to all the sections, section 1, section 2 and section 3. For all these sections, P magnitude of force which is tensile in nature, that is acting, and as material is same, Young's modulus is E. So that's why that is the common factor we have taken common. Well, dl3 is equal to P upon E into bracket L3 upon A3. Then dl is equal to dl1 plus dl2 plus dl3. We will write that total elongation of the bar will be addition of these three equations. If we take P upon E as common from all of them, this will become L1 upon A1 plus L2 upon A2 plus L3 upon A3. So total elongation of the bar, that will be calculated based on this formula. dl is equal to P upon E into bracket L1 upon A1 plus L2 upon A2 plus L3 upon A3. If suppose the case is different one, it's in case suppose material is different, for section 1 if different material is used, for section 2 different material is used, and section 3 if suppose different material is used, then Young's modulus will not be same. In that case Young's modulus will be E1, E2 and E3, but force will remain as it is. In that case, if second case we are considering here, if material is different, the same equation in order to calculate the elongation of the bar dl will be considered as P we are taking common here. Equation will become L1 upon A1 E1 plus L2 upon A2 E2 plus L3 upon A3 E3, where with usual notations E1 will be Young's modulus of the material for section 1, E2 will be Young's modulus of the material for section 2, and E3 will be Young's modulus for material for section 3. Is it okay? So all these three sections, if Young's modulus is different, then this elongation dl will be calculated based on this formula, but P will remain as it is. Is it okay? So bars of varying cross section, in that case how to identify the elongation, this is the second type of example which we have seen in simple stress and strain chapter. Then the third kind of examples which we have seen in simple stress and strain is depends upon the principle of superposition. So third kind of example which we have seen. So that kind, so third type in simple stress and strain. The third type was principle of superposition. So principle of superposition, inside that what conditions we have considered in principle of superposition. We'll take one example for principle of superposition. Suppose this is any bar with different sections. Suppose this is section 1, this is section 2 and this is section 3. As usual, we are considering section 1, section 2, section 3 Maybe that sections are having cross-sectional area uniform or cross-sectional area varying. Okay. So if we are taking one example that now cross-sectional area is same here, and if we take that 50 kilonewton amount of force is acting on this section here, if suppose 20 kilonewton amount of force is acting here at this point, 10 kilonewton of force is acting here at this point, then at this point we will have to consider this as 20 kilonewton amount of force, because in principle of superposition always there is one assumption or there is always one fixed criteria that whatever the force is moving toward the right side are same forces moving toward the left side. Is it okay? So summation of forces moving to the right side are same as summation of forces moving to the left side. So if here we will consider the total force acting, so force on all sections or force on each section, if we are interested to identify here, then initially we are going to consider this portion as section 1, this as section 2 and this as section 3. But before that, let us consider that what are the summation of forces moving toward the right side. Toward the right side force is only one force and its magnitude is 50 kilonewton. And what are the forces coming toward the left sides? Three kind of forces are there moving toward the left side. What is the addition of all these forces? 20 plus 10 plus 20, and that addition is 50 kilonewton. Is it okay? So for section 1, forces on each section when we are identifying, if suppose we are taking this section 1, and for this section 1 as this 50 kilonewton amount of force is acting and which is compressive in nature as far as concerned with that section 1, then same amount of force will be here at this end and this will be 50 kilonewton. Similarly, if we are identifying the force coming individually on this section 3, then for this section 3, this is the 20 kilonewton force acting here. We are considering this as 20 kilonewton. As far as concerned with this section 3, this will be also again compressive in nature. Okay, so this is 20 kilonewton is compressive in nature. If we are coming to this section 2, then for this section 2, if we are interested to identify the force acting on section 2, because there are many number of forces actually acting on this total element, total bar. For that, what we are doing? We are taking one line here. And by producing this line, if suppose this is in section 2, that's why I will write 2 line which is passing through this section 2. Then for this line to the left side, we are considering summation of forces. So what is the summation of force about left side of this line 2, 2? If 50 kilonewton is moving toward the right, here I will write 50 kilonewton is the amount of force moving toward the right, and 20 kilonewton is the amount of force moving toward the left. Then what will be the summation of this force? The summation of this force will be considered as 50 minus 20, because 50 is moving in toward the right side and 20 is moving toward the left side. So summation of force will be 30 kilonewton. And what will be the dominating direction? So dominating direction will be the direction of 50 kilonewton. So 50 kilonewton minus 20 kilonewton, this is 30 kilonewton amount of force and the direction of 50 kilonewton will be considered here. On another side, now equal force, that is 30 kilonewton, definitely will act. But if we are interested to identify that whether this force is 30 kilonewton or not, let us, I am taking one more line on this end. Just 30 kilonewton, that is going to come on this side also, but in order to check that whether this is following or not, if I am considering all the forces to the right side of this line, of this section, suppose I am considering as this is section 2 that's why 2 section to the right side, then 10 plus 20, so 10 kilonewton amount of force and 20 kilonewton amount of force, both are moving to the left side. The summation of both the forces is 30 kilonewton. So for section 2, if we are drawing this free body diagram, then for the section 2, this free body diagram here will consider 30 kilonewton amount of force, and this is also compressive in nature. So 50 kilonewton on section 1, 20 kilonewton on section 2, and 30 kilonewton amount of force acting on section 2. So remaining calculations will be same as previously discussed by us. That is, if we are interested to identify the elongation dl, then that dl will be again dl1 plus dl2 plus dl3. But here force is not constant, but force is varying force. Means for section 1, different force we are considering now. P1 is the magnitude of force acting here. So here we will refer P1 is equal to 50, that is negative because compressive in nature. So tensile forces we are considering positive sign, compressive forces we are considering negative sign. So P1 is minus 50, then P2 here it is minus 30, and for P3 we are considered here as 20 kilonewton, which is also compressive in nature, so minus 20 kilonewton. So total elongation or total contraction will be given by this dl. dl is dl1 plus dl2 plus dl3. With usual notations, again dl will be considered as P1 L1 upon A1 E1 plus P2 L2 upon A2 E2 plus P3 L3 upon A3 E3, where L1 is length of section 1, L2 is length of section 2, and L3 is length of section 3. As cross sectional area is same, so here A1, A2 and A3 will remain same. So A1 is equal to A2 is equal to A3, which is equal to A. Force is different for each section, length will be different for each section. If material is same, again E1, E2 and E3 will be same. Is it okay? In this case also material is same or material is different. Is it okay? If material is same, then Young's modulus per section 1, Young's modulus per section 2 and Young's modulus per section 3 will be same. So here E1 is equal to E2 is equal to E3 is equal to E if material is same for each section. And if material is different, with notation C1, A2 and A3 will be Young's modulus per section 1, A2 will be Young's modulus per section 2, Young's modulus per section 3. Is it okay? Area is same, that is already cross sectional area is as it is here. So for this particular bar, the principle of superposition means if suppose the forces are acting in between the sections at different locations, then how to identify the elongation present inside the material. So that kind of variety we have considered as principle of superposition. Okay. Then next, fourth kind of variety which we have seen in this chapter 1. So that is statically indeterminate bars. So statically indeterminate bars means what? So static indeterminate bars means the type of bars for which their motion is restricted from both ends. If suppose this is any bar, if it is not allowed to expand, then we are considering this kind of example as statically indeterminate bar. If we take the case, suppose any bar with two different sections, so this is section 1 and section 2 is present here, and in between that section, if some magnitude of force is acting, suppose 50 kilonewton amount of force is acting in between this section 1 and section 2, then this will become a statically indeterminate system or statically indeterminate bar with two different sections. And for section 1, this 50 kilonewton amount of force, as well as on section 2, this 50 kilonewton amount of force will act. So this 50 kilonewton is not the magnitude of force acting on section 1 only or magnitude of force acting in section 2 only, but that 50 kilonewton amount of force is acting on both sections, section 1 as well as section 2. So here, once again we are considering the free body diagrams to identify the values of this force exactly acting on section 1 and section 2. Here our two assumptions, out of which first assumption always to solve this kind of example is that the first assumption is if dl1 is the elongation produced in section 1, dl1 is the elongation produced. Maybe either I will say not elongation, we will use the word deformation. Deformation in section 1, and if suppose dl2 is the deformation in section 2, then addition of these two deformations, if suppose dl is the total deformation, we are considering this as total deformation. If dl1 is deformation in section 1, if dl2 is deformation in section 2, the total deformation is given by dl. So here total deformation dl will be considered as addition of deformations for section 1 and section 2. So dl1 plus dl2. But what could be the value of this dl? What will be the total deformation? As the case is statically indeterminate bars and as it is restricted from both the ends, no any kind of deformation for total bar is allowed, then what will be the value of dl? dl will be equal to 0. So dl is equal to 0. So here our first assumption or first equation will get formed, that 0 is equal to dl1 plus dl2, or with its usual notations, if we are considering as dl1 is equal to p1l1 upon a1e1 and dl2 is equal to p2l2 upon a2e2, then dl is equal to 0. That's why p1l1 upon a1e1 plus p2l2 upon a2e2 is equal to, considered to be equal to 0. Is it okay? Now if we consider that material is same Therefore, section 1 and section 2, if material is same, then Young's modulus will be same. If cross-sectional area is again same, if that is different, then we will consider it as different. But if it is considered to be same, so if cross-section and material is same, then we will consider as A1 is equal to A2 is equal to A, E1 is equal to E2 is equal to E. So A1, E1 will be considered as AE, and A2, E2 will be also considered as AE. If we take common AE, then this will become, suppose P1 L1 upon AE plus P2 L2 upon AE will become equal to 0. By taking AE as common, this equation will become P1 L1 plus P2 L2 is equal to 0, where L1 is considered to be length of this section 1 and L2 is length of section 2. L1 will be considered as length of section 1 and L2 is the length of section 2. Now this is one equation which is generated based on the assumption that total deformation is equal to 0. But here one more assumption is possible. The second assumption which is possible with this is based on the free body diagram, and in that free body diagram, if we consider the section 1, here we are considering that section 1 on which tensile force of magnitude P1 is acting. Similarly, on section 2, the tensile force of magnitude P2 is acting. If now I am giving here name as, suppose this is A, B and C. Length AB will be L1 and length BC will be L2 in that equation. If that is given, L1 and L2, that both lengths are given to us. Then here, the P1 is acting on section 1, that is on section AB, on the portion AB, and for the portion BC, if suppose this P2 magnitude of force is acting, then being a B as a common part for both the forces, but on this portion, section B, P1 amount of force is also acting on this section. Second, on B, this P2 amount of force is also acting. As we have considered the direction of 50 kN toward the right side. Okay. So here we will consider that P1 minus P2 is equal to 50 kN. That is, 50 kN is the total magnitude of force acting at the portion B, and this B portion means P1 is toward the right side, P2 is considered toward the left side, but actually 50 kN is acting toward the right side. That's why we have considered, we have written equation P1 minus P2 is equal to 50 kN. Is it okay? If suppose it happens that this 50 kN force is moving toward the left side, if it is given, if we assume that the force is given moving toward the left side, then what will happen? In that case, this left side direction and P2 direction will be same. In that case, our equation will change as P2 minus P1 is equal to 50. But presently we are writing as P1 minus P2 is equal to 50 because the direction of P1 and direction of 50 is same. That is moving both. Our assumed direction of P1 toward the right side and actual direction of 50 is toward the right side. Our assumed direction of P2 is towards the left side. So that's why this is negative minus P1 minus P2 is equal to 50 kN. So that will be second set of equation This will be considered as a first set of equation. P1 L1 plus P2 L2 is equal to 0, where L1 and L2 are known, lengths are given to us. In that case, AB is length L1 and BC is length L2. Then two equations in between P1 and P2 will establish. One equation in terms of this deformation and another equation in terms of this free body diagram of the forces. Then by solving this equation 1 and this equation 2, we can identify the P1 as well as P2. Okay. When P1 and P2 are known, in that case it is easy to identify DL1 as well as DL2, because already we have considered the DL1 as P1 L1 upon A1 E1. P1 is known now, L1 is also known, cross sectional area and Young's modulus of material is available. Okay. So it is possible to identify the elongation present in section 1 as well as elongation present in section 2. Total elongation is being same. If we are interested to identify the stress sigma 1, if sigma 1 we are considering as stress in section 1, then sigma 1 will be calculated based on this evaluated values P1 upon A1. For section 1, stress will be calculated as P1 upon A1. P1 will be calculated from equation 1 and equation 2, and stress sigma 1 will be calculated as P1 upon A1. Is it okay? So this about the statically indeterminate bar. So this is one kind of example which is present inside a simple stress strain. Then fifth type of example which we have seen in simple stress strain, that is composite bars. So fifth type of example which we have seen, this fifth type we are considering as composite bar. Inside this first type of example was simple stress strain, second type of example bars of varying cross section, third type of example was principle of superposition, fourth of statically indeterminate bars. And in case of composite bar, we are taking, in general there are varieties of example in case of composite bars, but in general we are considering if the bars are parallel to each other. If suppose these are two bars which are parallel to each other, up till now for section, for all four kinds of varieties of example, there were the sections were in series with each other. But in case of composite bar, these sections are now parallel to each other. This one is suppose steel material, and if suppose this is copper material, these two materials are there. Then if rigidly at its one end these are fixed, at the top they are supported, and at the bottom if they are rigidly fixed to any fastener, and if suppose P amount of force is acting on this both the bars, then that kind of system is considered as composite system. Is it okay? Two different materials are present. Not only two but more than two materials are also possible. So if suppose elongation of that material happens, then due to this elongation of the material, whatever new changes in that steel and copper bar are going to happen, we are regarding that with DL1. So DL1 will be considered as elongation present inside bar 1 as well as elongation present in bar 2. Then what will be the assumption in case of composite bars? In composite bar, our first assumption is that elongation produced in, suppose we have taken the example of here steel and copper, and P amount of force is acting here, then elongation present inside the steel is same as elongation present inside the copper. Okay. So elongation present in first material is same as elongation present in second material. Okay. So as usual, elongation is nothing but PL upon AE. So that will be force. So we will consider here as P steel, L steel, A steel and E steel. That is elongation for steel rod. And here if we consider for copper, then PL upon AE for copper bar. Okay. So in this case, the first equation in between these forces will be established based on this steel and copper, because length is common for both the case, steel and copper. Length is already same. As in this particular case length is same, we are cancelling this length. Cross sectional area of steel is given to us and Young's modulus of steel is given to us. Similarly, cross sectional area of copper and Young's modulus of copper is given to us. Then one equation will get established, that is P steel is equal to A steel E steel upon A copper E copper into P copper. So this is the relationship between P steel and P copper. So this kind of one relation will get established, and second relation will get established based on the assumption, with the second assumption that total force, if it is P is acting on this both the bars, then P is given as P is equal to P steel plus P copper. Means total force if P is present, out of which some amount of force will get contributed by steel and some amount of force will get contributed by copper. So P is equal to P steel plus P copper. This will be the second set of equation. If total amount of force P is given to us, then with this equation 1 and equation 2, we become able to identify the forces acting on steel bar as well as copper bar. Once successfully we identified the value of steel as well as copper bar, forces acting on steel bar and copper bar, or the amount of force contributed by steel bar and copper bar, then we will be able to identify value of DL1 as well as stresses present inside the bars. Okay, so stresses will be again, if suppose we are interested to identify stress in steel, it will be force in steel and cross sectional area